Welcome to Waidsum Academy. Today we'll be looking at physics chapter 9, thermal properties of temperature. Okay, chapter 8 is on the way, so quickly let's take a look at chapter 9 and look at the thermal properties of materials and their temperature. Okay, without much ado, let's begin. Now, the first thing we do is to quickly the big questions like our learning outcome, learning objectives. Why do we think railway tracks shown in the photo has barcode as barcode? Why is it barcode? You see Buckley of the railway track. Why do you think so? Because of expansion, obviously because of expansion. How can we tell from this photo that large forces have acted on it? Because you can see bent, right? Large forces have acted on it because you can see bent that is happening to the train and so on and so forth. Now, why is it important to prevent buckling of rail tracks? Because it can make the rail to derail, right? It can make the rail wheel to derail from its track. The track should be as designed. So to do this, we have to mitigate against the effects of thermal expansion. We have to plan expansion and contraction that it will happen to metals when they're heated. During the sunny day, the metals are heated. During the cool winter time, the metals are contracted. They contract. So the expansion and contractions are natural effects that will happen to metals that are exposed to extreme temperatures. So in design, in engineering, you have to design to mitigate against these kind of problems that will come up, okay, as time progresses. Why is it important to prevent them? Because it can lead to accident, can make the rail to derail from the track. Can you think of ways to prevent? Of course, we want to. That's what we want to look at. Now let's take a look at the first aspect, the thermal expansion 9.1, the expansion that happens to substances. Here we'll be asked to describe extensively the thermal expansions of solid, liquid, and gases at constant pressure. Pressure kept constant. What happens to the solid, liquid, and gases when they are heated? Is that okay? And then that's the first part. The second part is to look at some of the ways or everyday applications and consequences of thermal expansions. So without wasting time, let's go to the first aspect, which is the expansion itself. What happens when materials are heated? What happens when materials are heated? I think we should take highlighter to be showing some of the significant parts that we need to show. Now, what happens when materials are heated? When materials are heated, they will increase in volume. They will increase in volume, meaning they will expand. When you heat any material, it will increase in volume. The size will get bigger. Okay, that means that's what we call expansion. When materials increase in volume when they are heated, right? That terminology, increase in volume, is what we call expansion. That increase in volume is what we call expansion. Then, another thing that happens when they are heated is that the greater the temperature rise, the greater the expansion. For example, if you heat something from 50 degrees Celsius to 80 degrees Celsius, comparable to that same thing, providing the same metal, if you are applying 100 degrees Celsius, it's going to double. The expansion will double. Okay, the expansion will double because you've doubled the amount of temperature rise that has happened to the metal. Now take a look at this metal. Before heating, this could easily pass this ring. This metal object could easily pass this ring, right? But after heating, it finds it difficult to pass through. After heating, it passes it because what happens? Because this ball has been heated and it has expanded. The metal ball has been heated. It has increased in size. It has maybe not noticeably from your naked eyes, but alternatively, if you try it with the same ring that it used to pass through, it only cannot easily pass through because the metal ball has expanded. Okay, now for solid, yes, that's what happened to solid. But in liquid, the expansion is greater than in solid. Why? Because the particles of solid are very tightly put together. So if you heat, temperature will cause a little bit vibration, a little bit here and there. The expansion is very minimal compared to liquid. When you heat a liquid, the particles of the liquid easily can move about easily when you heat it. So you can see the expansion. Let's say, take a look at in the liquid gas thermometer. Let's say we're using alcohol as a thermometric liquid in this thermometer. This is a thermometer. Now, when you heat this thermometer, you can see the initial flow of this alcohol in this liquid glass thermometer is from 0 or from the bulb to 10 degrees Celsius. But when you heat this thermometer, when you heat this thermometer, the alcohol in glass or the alcohol in the thermometer expands from 10 all the way 10 to 60. So there's 50-degree expansion from 10 to 50. That is the expansion. Because liquid expand greater than solid. Expansion in liquid is greater than that of solid, okay? Because the particles are a little bit free to move a little bit. So when you heat, the volume easily expand, get bigger, okay? Compared to gas. In the case of gas, when little temperature increase cause the air around us to get warm or expand very fast, and you see bubble coming out. So in the case of gas, expansion in gas is greater than that of liquid, and the one in liquid is greater than that of solid. So when you heat solid, liquid, and gas, they expand. Okay, that's the first point. Now let's go to the second point. Why do solid, liquid, and gases expand by different amount? Why do solid, liquid, and gases expand by different amount? This is based on the arrangement of particles in this solid, liquid, and gas. This is based on the arrangement of particles in solid, liquid, and gas. Expansion, gas expansion is greater than liquid expansion, which I have itemized already. Gas expansion is greater than the expansion in liquid, and the expansion in liquid is greater than the expansion in solid. The expansion in liquid is greater than the expansion in solid. Why? Because for the same amount of temperature. We are not saying if you vary the temperature, that's not what we are talking about. If you give them equal amount of temperature, that's the condition. That's the condition. If you give them equal amount of temperature, this is what we are talking about, right? This is what we're talking about. If you give them equal amount of temperature, then the expansion varies. It varies, okay? The expansion varies if you give them equal amount of temperature. Now, we say gas expand because the particles are further up, state of matter get bigger compared to that of liquid. Liquid is greater than that of solid because particles in liquid are a little bit widely spread apart compared to that of solid. Solid expansion a little bit, which may not be too visible. Particles do not expand, but the volume is what expands. The volume is what the volume that the particle occupy does. The particles themselves don't expand. They move and they create a bigger volume. For example, take a look at this. This is the liquid. When you heat it, before heating, when you heat it, it expands and you can see the height get bigger. The volume of the liquid gets bigger. It's not the particle that gets bigger, but the particles are able to move further from each other and make it the volume of the liquid bigger. Okay. Now let's move on to the next one quickly. Of expansion. No space to expand will lead to large force may act. If you don't create space, you take a look at this railway line. Take a look. This is called expansion gap. They will be able to expand and still be okay. But if you don't create this expansion gap, what happens is that these metals, when they're heated, there will be a greater force that's constricted them. So we always leave expansion gap in length of a railway so that when they expand, they have a space to act, to get their linearity, and when they contract, they can still go back to the original form. Is that okay? Now let's take a look at this. Originally, when you expansion gaps in a bridge railway, they will open up, and this will make the bridge to last longer. Not only this one, also the bridge will make it to sit on a roller supporting edge. The bridge can roll this metal tray wheel. We have the metal axle and we have the metal wheel itself. Now what we do is that before expanding, you can see this axle is not able, it's bigger than this hollow space. So it's not able to go in here. It's not able to go in. Okay? So after expansion, it can shrink. It will shrink. So after expansion, after you heat it, it will expand to be able to, then when it contracts, it shrink, it can fit in here. It can fit in here. So these are shrink expansion, one of the application and usefulness of expansion. Gap left in railway is one of the application. Bridges, expansion gaps in bridges are one of the rollers support in bridges, also one of the applications of expansion. Now let's take a look at this expansion we mentioned in railway, in bridges, and in shrink fittings. So he say this. I think these are questions, right? He has given us questions. He say explain the application and consequences of expansion in railway. Okay. Explain the application. Okay, just a question for us to look at. Explain the application and consequences of expansion. Railway lines. Some railway lines have expansion gaps to allow, like what we said, to allow what? To allow expansion when the line gets hot. When they get hot, There are lines, there are gaps for them to expand that will still fit in without creating that large amount of force. Modern railway lines do not have this gap. Modern railway lines do not have this gap. This is to allow the trains to move more smoothly, okay? Because the previous one, you allow the gap for expansion. Modern ones don't have this gap, but they're choosing the smooth journey of the train over expansion gaps, okay? These lines are designed to fit in tightly on a hot day. They are designed to fit in tightly. Even on a hot day, they fit into themselves. And on a cold day, they contract and still be okay. Now, another application of expansion is in bridges, like we've shown in the diagram. Bridges also expand and contract when you change the temperature. During the hot day, it expands. During the cold day, it contracts. And expansion gaps at the end of the concrete bridge can be introduced to allow to solve the problem. A gap in this metallic part that is, every bridge has this kind of metallic part created, okay, and there are small gaps. That's why when you drive on the bridge, you hear gugum, 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 because of this thin metal that has been placed on the road, on the bridge. And also the rollers, as if the bridge also slide a little bit. You have the roller support on the bridge. Okay, so these are some of the applications of expansion. Another one is shrink fitting, the one we've talked about, that we hit the axle to be bigger. We hit the axle to be bigger than the normal size of the wheel, so that when it cools, it's able to fit into the wheel. You hit it to be bigger than the wheel, so that when it cools, it's able to fit into the wheel. Okay, so this is for shrink fitting. So we've itemized 3 applications here. One is the railway application. Tool is in answer this question. What evidence is there that forces caused by expansions are large? What evidence is there? Okay, here you discuss the force, and so here is the answer. You pause the video and see the solution that we've provided. Now let's move on to the next one. The second part of this lesson is called specific heat capacity. So the second part of this lesson is called specific heat capacity. Here we're going to know that a rise in temperature of an object increases the internal energy of the object. When you heat anything, the particle gain kinetic energy. So every particle that makes up that substance, when it gains energy, the sum of all the energies of the particles of that substance is what we call the internal energy. The sum of all the energies of the individual particles, when you sum all the energy each individual particle gets, when you sum them together, becomes the total internal energy of the particle. So we need to know that. And then we should be able to describe an increase in temperature in terms of an increase in the average kinetic energy. So when temperature increases, the average kinetic energy of the particle also increases. And then we should also recall the use of the equations of specific heat capacity, and describe an experiment to measure specific capacity. So this is the aspect we want to learn in this lesson. Now let's take a look at the first one. What is internal energy? We've already mentioned. The internal energy is the total energy of each of the particles that makes up that substance. So every single particle, if there are thousands of particles in one substance, in one matter, then if you sum all the energy up, you get the total internal energy. Now, if you heat this particle, the energy increases. The average kinetic energy of each particle increases. Hence, the internal energy of the system increases. The internal energy of the system increases. Thermal energy from the flame, you take a look at this. We have water, we are boiling water. We put water in a Bunsen burner, and we apply the heat. So the water gains the thermal energy from this flame. It's passed on to the water. The water gain average kinetic energy. So each particle of the water gain energy, and then further increase. So the internal energy of the water increases because the energy from the flame, the thermal energy from the flame, is passed to each of the particle of the water. Okay. Now the internal energy of the water increases. Why? Because you're passing the energy of the flame, the thermal energy of the flame, to the energy of the water. So the internal energy of the water increases. Okay, whenever you heat water, the internal energy of the water increases because each of the particles gain kinetic energy, and therefore it increases. Now let's go to what is specific capacity. Specific capacity is the amount of thermal energy required to raise the temperature of a unit substance, of a unit mass of a substance. The mass usually like 1 kg of a substance through 1 degree Celsius or through 1 degree Kelvin. So what does this statement mean? We say the amount of thermal energy. The amount of energy you need that is required, that is needed. You can use the word needed, required, to raise the temperature of a unit mass of a substance. To raise, let's say, a unit mass of water. You're just taking 1 kg of water, okay? To raise the temperature of a unit mass of water through 1 degree Celsius. Meaning, if the temperature was 24, and let's say 22, the temperature of the water was 22, the amount of energy you need to heat it to 23, from 22 to 23. 1 kg of water, you take 1 kg of water, you measure 1 kg of water, for example. Okay? Okay, you measure 1 kg of water, and 22 to 23, because we said only through 1 degree Celsius. To heat it from 22 degree to 23. That's what we call specific heat capacity. The amount of energy you need to heat 1 unit mass of a substance, you must measure the mass. If you don't talk about the mass, you are talking about thermal energy, not you're talking about the thermal energy or the thermal capacity. You're talking about the thermal capacity. You're not talking about specific heat capacity. So you must measure the unit mass, the amount of energy that is required, to raise the temperature of 1 unit mass of a substance. 1 unit mass, 1 kg, 1 kg. When we say 1 unit mass, we say 1 kg of a substance through 1 degree Celsius, meaning to heat it from 22 to 23. Take 1 kg of water. What amount of energy will be able to heat it from degree 22? Let's say you take the temperature of the water with your thermometer. You measure the temperature of the water. Let's say the temperature of the water is 22 degrees Celsius. What energy, how much amount of energy can heat it from 22 to 23? 1 kg of water, how much energy is needed to heat it from 22 to 23? That energy is called specific heat capacity. That energy, that small energy you supply, thermal energy you supply to heat 1 kg of water, 1 kg of a substance. It may not necessarily be water. 1 kg of a substance, 1 kg of a substance from not necessarily 22 to 23, meaning whatever temperature you're looking at, just 1 degree rise. 1 degree rise. If the original temperature is 10, meaning it moves from 10 to 11, just 1 degree rise in temperature. That energy that caused that 1 degree rise of 1 kg of a substance is what we call specific heat capacity. So they commonly use this thing is given as, okay, let's first of all give the formula. The formula is of specific capacity is the energy you need. That's why we say the energy required, or the energy, we can use delta E. Energy required or the energy needed. Okay, it's up to you the English you want to use. The energy needed or energy required to heat a unit mass of a substance of 1 kg through 1 degree Celsius. Okay, so there's mass. You need to heat a unit mass. So I write M, the mass of the substance, through 1 degree Celsius. So change the temperature. There must be change the temperature. Why change the temperature? Because it's moving from 22 to 23. There's a change. So to find the change in temperature, you say 23 minus 22. So you get 1 degree Celsius in this regard. Okay. So through change in temperature. Change in temperature is delta T. So I put delta T here. Or delta theta. Some textbook will use theta for temperature. So this is the formula for specific. For me, I always write small subscript S to show a specific capacity. I say Cx equals to the energy required to heat a unit mass of 1 kg of a substance through 1 degree Celsius. So this is the formula. We can call this equation 1. If you cross multiply, you get the energy formula of it. You get the energy formula, which most people remember first. It is the energy formula that most people remember first, which means delta E is equal to, you cross multiply, M mass times specific capacity. Specific capacity, this S is together with specific capacity. You can write only C. You can write CS or you say only C. Then times delta T. Most textbooks just use C for specific capacity. Remember, this C is a symbol for specific capacity. This is the mass of the substance you're heating, and this is the change in temperature, how much rise it rose, and this is the energy. You write equal to, sorry, you have to put equal to here. This is equation 2. They are same equation, okay? Okay, here are some specific capacity for different materials. Lead is 130. What is the unit? You must know the unit. You can derive the unit from the formula if you don't know, if you don't remember. Energy is Joule. So if I want to derive the unit, I will just say Joule. I'll say J, Joule, per. Divide means per. Mass is kilogram. And this one is a Kelvin. kilogram per Kelvin. Kilogram per degree, either per degree sensor or per Kelvin. Okay, this is the unit for specific capacity. Now, these are different specific capacity for different substances. Please, you must pay attention. This is very important in IGCSE. The calculations are always here. Okay, you're going to get calculation from here in the exam. So please pay attention how to use the formula, how to remember the formula, how to write the units for specific capacity. Now, different materials have different specific capacity. For example, lead is 130 joule per Kelvin per degree Celsius. Mercury is 140. Brass is 1. You don't have to memorize. So it's either they ask you to calculate it or they give it to you. Zinc is 390. Copper is 400. Iron is 460. Glass is 670. Aluminum is 900. Methylated spirit is 2,400. Water is uniquely high, 4,200 joule per degree per kilogram per degree Celsius. So water is seawater is 3,900. Seawater because it contains salt. It's not a pure water. It's 3,900. Water is unevenly high, unbelievably high. We will not expect that a liquid has so much specific capacity, but because it's the nature of what God has done. So water is 4,200 because we've done this experimentally to find water has a high specific capacity. Now let's take a calculation because the exam comes from the understanding, the calculation, and the experiment, paper 6. Okay, let's quickly take a look at the calculation, which is for paper 4 or for paper 2. Paper 2 is multiple choice for those who are doing extended, and paper 1 is core for those who are doing core. Okay, paper 2 is multiple choice, which is extended. Paper 1 is core, is multiple choice for the core student. Okay, so but these questions I think they evolve extended extensively. Now, it says calculate the temperature change of 1 kg of, I'm talking about Cambridge IGCSE, okay? You'll be wondering which exam was I talking about. It says calculate the temperature change of 1 kg, you see the mass is 1 kg, temperature change of 1 kg of copper when it's supplied with 4,200 joules of thermal energy. The energy is given to us. In most cases, we calculate the energy first. But in this case, energy has been given to us. So delta E is given to us, right? We say delta E. Okay, to be fast, let's just resolve to the formula, the energy formula. The energy formula is delta E is equals to mass times specific capacity times change in temperature. Like I told you, some textbook, they use theta as temperature. Okay, you can use theta. You can change it as temperature change, or you use T. It's okay. Anyone you use is okay. It's just a symbol for you to remember a formula. Okay, so we say the change in energy is equals to mass times specific capacity times change in temperature. Okay, so they give you the energy, but they want you to calculate what? The change in temperature. So you must know what the question wants from you. The question wants this one, right? And of what? Of copper. They didn't give us the specific capacity because this is a textbook question, right? So you go to the table and take the specific capacity of copper. This they did give that parameter. You must list out the parameter that is given. So we go to the textbook and we take the specific capacity. We're going to use 400. Copper is 400. So we're going to use 400. So the energy is what? The energy is 4,200 joules. Remember, this is not the specific capacity of water that we talked about. It's just a coincidence that the energy for this particular question is 4,200. So you order energy, you write 4,200. The mass is 1 kg, so we write 1 here. The specific capacity C is 400, so I write 400 here. And then change the temperature is what they ask us to calculate, so you put change the temperature. 1 times 400 is 400. So you make this one the subject, it becomes delta T, delta theta, which is change in temperature, is the energy divided by, is the change in energy divided by the mass and the specific capacity. Because we are making this one the subject. Okay, a bit laggy. Change in temperature. Change means delta. We use this is called delta. Okay, see, is laggy. 10.5. 10.5 degrees Celsius, so you have to write the unit. In physics, most people, they lose their mark because when they write, they don't write unit. Because you are doing change in temperature, so you write the unit. Okay, you write the unit, 10.5. Okay, so that's for this question. Let's move on to the next one. This one is an experiment, right? Experiment, you want to investigate. Objective is to determine specific capacity of a solid. What do you do when you want to determine the specific capacity of a solid? You take a solid, you create two holes inside the solid. Okay, this one is paper 6 because they ask you to use and describe an experiment to determine the specific capacity of a solid. What you do, you do something like this. This is the kind of diagram you draw. You should picture this diagram in your mind. Okay, you take a solid, you create two holes. One, you're going to put what? A heater. And the other one, you're going to put what we call the temperature sensors to sense the change in temperature. You're going to put a temperature sensor, you're going to put a heater. Okay? And then this heater you connect to electricity because this is how you supply, right? You connect to electricity. You see your ammeter to measure the current, voltmeter to measure the voltage. This you can just do electrical source the way you know it. Okay? When you do electricity, you see this is not a big deal. Okay, so we connect to electricity. This is electricity. And then that's the, so first you write your objective or you say aim to determine the specific capacity of a solid. Final temperature minus initial temperature. So we're going to use that. Final temperature minus initial temperature to calculate from this sensor, from this temperature sensor. We're going to sense the initial, we're going to record the initial temperature and the final temperature. We're going to determine our power and our energy from here. Okay, first of all, the power equals to current times voltage. This electrical power, because we are using electricity. Electrical power is equals to a current that is flowing, because that's why we put ammeter to measure the current, and we put a voltmeter to measure the voltage. So the current measured here is called I, letter I. Current is represented in physics. When you do grade level, you're going to do current electricity. The current that is flowing is I. Current that is flowing through the electrical source is called letter. The symbol is I, and is measured with an ammeter. The symbol of ammeter is A, and the voltage is measured with a voltmeter, and the voltage is also V. The symbol is V, and the unit is V. Okay, so the power is determined by, is calculated by the current times voltage. When you say IV, it means current times voltage. And the time used, you have to, you record the time. You have to record the time used. So to get energy, you must multiply, because look at it. Power is, let's write, power is energy over time, right? Power is energy over time in normal physics. Power in mechanical physics. Okay, power is energy over time. Remember, we already got the formula for power, IV, energy over time. So if I cross multiply to get my energy now, because we need the energy in specific capacity. Energy is what? Power times time. If I cross multiply, energy will be what? Power. These are calculation. When you do experiment, you have to show the calculation. Energy is power times time. Power times time. Now remember, you already have the formula for power. We say power is IV. Power is IV. If I substitute in place of P, if I substitute the electrical power, energy will now be what? IVT. Energy will be what? I want to replace the P, this letter P, with the formula for power, which is IV. Then you put the T. So the electrical energy, which you're going to learn in later chapter, is IVT. This is the energy, electrical energy supply for this heater. Okay, this is the energy we supply that we use for this heater. After you've done that, the specific capacity of the aluminum will be given by C. Right? The specific, you label it. The specific capacity is given by C. And then after that, you calculate the specific capacity based on what we have told you already. That specific capacity is the energy you measured just now, which is IVT. So times change in temperature. The mass of the substance, you have to measure the mass of the block, this solid, or mass of the solid. You have to weigh it in a beam balance. You have to weigh this one in a beam balance and record the mass of the block. And then that mass times the change in temperature, the temperature sensor has helped you to note the first temperature and the final temperature. That change in temperature, you get your specific capacity. You calculate your specific capacity. So you find an experiment to describe all of this. You write in paper 6 to describe all of this. Now let's take a look at the question. Let's take a look at the calculation question quickly. Okay? Now it's an electric heating coil supplies 50 watt. This is the power, watt. We need the energy. To get energy, you say this power divided by time. Remember that. This one, power is 50 watt. Power is 50 watt. That's not the energy we're looking for. Okay? We go to find the energy, 50 watt. 50 watt. Watt is the unit of power. Watt is the unit of power. Okay? So remember, energy is power over. Energy is power, because power is energy over time. Power is energy over time. So when you cross multiply, power is energy divided by time. Mechanical is energy divided by time. So if I cross multiply, energy will be power times time. Energy will be power times time. So meaning they've already given me the power. When they give me time, I will multiply them, I will get my energy. The power is 50 watt, I will get the, so it's an electric heating coil supplies 50 watt of power to a metal block of 0.6 kg in 90 seconds. So they've given you the time. So you write mass is 0.6 kg, you write time, you bring out all your parameters. Okay? Time is 90 seconds. Power is given to us 50 watt. And then time is given 90 seconds. So we use power at time to calculate energy. The view mass to be 0.6, and then change in temperature is 45. The final one minus the initial one. The final one minus the initial one, meaning 45 minus 20. 45 minus 20 will give me 25. So my change in temperature is 25. My change in temperature is 25. Now the thermal energy supplied by the heater is what? 50 times 90, which gives you the energy. 4,500 joule. These are energy we're going to use for our calculation. Remember, the energy is equal to mass times specific capacity times change in temperature. Mass times specific capacity times what? Change in temperature. Remember what this one is. PT means energy, actually. PT means what? Energy. Look at here. I wrote it. Energy is what? PT. So don't let that fool you. Be what you owe. Where is PT? When we did specific capacity, we did do PT. PT means energy, change in energy. So this one is energy. So energy equals to mass times specific capacity times change in temperature. Times change in temperature. The question says we should calculate what? Calculate the specific capacity. So we are looking for what? C. This small c here. Okay, so you make it the subject of formula. You make it the subject of formula. Meaning this one equals to PT over M times theta. That change in temperature. The specific capacity will be what? Will be this. Okay, they want you to calculate it yourself. Meaning you say this 4,500. So let's do that. 4,000 specific capacity, you make it the subject, C, is equals to PT, or energy. Okay, if you don't want to say PT, you just write your energy, if you are used to energy. Energy over what? Mass times change in temperature. Mass times change in temperature. Mass times change in temperature. So what's your energy? 4,500. So you write your 4,500. 4,500. Divide by 4,500 divided by your mass. Mass is 0.6. 0.6 times, what's our change in temperature? Remember, change in temperature is 25. Okay, because final minus initial. So times 25. 0.6 times 25. Then we divide 4,500 with the result we get from 0.6 times 25. I think that will give us 300 joule per kilogram Celsius. Okay, so that's that for that. Here's the experiment. I think I have described the experiment. They want you to investigate. You write the objective or the aim to determine specific capacity of a liquid. Then you have to connect the to electrical source. You measure the current and you measure the voltage. Voltage parallel to the source. Current can be in series. And then this is a lead to protect the heat loss. To protect, you seal it up with a polystyrene lead to avoid the loss of energy. And then the formula IVT. This IVT means energy. You know, right? Energy is IVT. I've derived all this formula equals to mass times specific capacity times change in temperature. Change in temperature means theta 2 minus theta 1. Don't be confused. We've done that already. So specific capacity, you make this one the subject. It means IVT over I is the current, V is the voltage, T is the time to calculate energy. If you want to calculate energy, it's IVT. I is the current, V is the voltage, T is the time. Then you divide by mass times change in temperature, you get your specific capacity. Let's move on. Here's the calculation because that one is just an experiment. Here's the calculation. You can just highlight what they want. They've given you 250, the mass of the liquid. They've given us 250, right? The mass of the liquid is 250 grams. This is in grams. That would be 180 seconds. If they give you 6 minutes, that's 360 seconds. You convert time to seconds. The final temperature has been given. Initial temperature is 80, final is 32. So you go to say final minus initial to get the change in temperature. You see, now the first one is calculate the power of the electric, the power. Power is IV. So let's show the calculation. I is the current. This one is the current. and V is the voltage. Because they give you all this value, I is the current, look at current is 3.5, and the voltage is 12.0. So you multiply 3.5 times 12.0, you get 42 watts. Remember the unit of power is watt. You get 42 watts. The second question says, calculate the thermal energy supplied by the heater in 360 seconds. Now they want the thermal energy. Energy is IVT. You write the energy formula, IVT. Power times time. Power, you already calculate power. Okay, since you already calculate power, no need to say IVT because it's like you will be gram, which is 0.25 if you change to kilograms. So you say 0.25 because you divide 250 by 1000, you get 0.25 times 14. So if you key this one in the calculator, first you multiply these numbers in the denominator, 0.25 times 14. Whatever you get, you say 50,120 divided by whatever you get when you multiply this one. Then you will get your specific capacity of the substance to be 4,320 to give you this one, okay? Key and see whether you get this value. Okay, so we move on to, this is a practice question. Pause this video and solve all these questions. This is how to become better. You never solve, you never get better. Okay, now we go to the last part of this chapter. Here, change of state. How you can change a substance from solid to liquid, from liquid to gas, creating a heating curve, and how you can change from gas to liquid by condensation, and then from liquid back to solid by freezing, okay, by freezing or by solidification. And this is what we want to look at in this section of this chapter, and then we call it a day. Now let's take a look at what happens to temperature when materials change state. When materials change, first of all, you look at the melting point of pure water. The melting point of pure water at standard temperature and pressure and 1 atmosphere is 0 degrees Celsius. Is what? 0 degrees Celsius. Is 0 degrees Celsius. The melting point and the freezing point is 0 degrees Celsius. Every pure water will melt, every solid will melt at 0 degree, and they also freeze. Water will freeze at 0 degree. Now, boiling point of pure water at standard atmospheric pressure of 1 atmosphere is 100 degrees Celsius. So water will boil at 100 degrees Celsius. So this is the experiment. If it doesn't boil at 100, then it means your water is not a pure water. It contains other impurities. Okay, this is a bossy burner. You heat the water and see how the temperature changes. You measure, you put a thermometer to measure the time, the temperature at which the water starts to boil. To measure the temperature at which the water starts to boil. Now, here is what we call the heating curve. Let's quickly take a look at the heating curve. Now, a solid is below 0 degrees Celsius, below. So -10 or negative whatever. And this is called ice. It's called ice. You know, ice is solid. So this part of the curve is what? It's called solid. It's called solid. So when you heat a solid, it will melt. So at 0 degree, it will comprise of both, some of them has melted, some are still, small particles are still in smaller lumps, not completely melted. So that stage 2, the whole of this horizontal line is called melting. You can see in melting, during melting, the temperature remains same. The temperature does not change. That's one thing. When you are explaining melting, you say the temperature does not change. The temperature of at that point does not change. At B, we call it B, the point B, the temperature does not change. But here, temperature changes. Temperature changes. Okay, as you are heating, temperature will change from probably -8 to 0. Temperature changes. But during melting, the temperature will remain same as all the solid change to liquid. As the remaining particle of solid change to liquid, temperature remains same. So when we were doing, there's a part we're going to do, latent heat of vaporization and latent heat of fusion. We're going to talk about it maybe later on. I don't know if it's still in the scope of IGCSE. If it's not in this book, it means it's no longer in the scope of, because this is a recently revised textbook that matches with the IGCSE scope. If it's not the latent heat of fusion and latent heat of vaporization, it means it has been removed from the IGCSE syllabus, Cambridge IGCSE grade level syllabus. Now, okay, here the temperature remains same. Okay, when you talk about latent heat, you talk latent heat of fusion is the heat energy required to melt a substance or to change a substance from solid to liquid without change of temperature, without change of temperature. Latent heat of fusion is the Heady heat. The Heady heat you don't see that is required to melt a substance from solid to liquid without change of temperature. If you see something's melting here, the temperature does not change because it's on the horizontal graph. It's on the horizontal graph. The value of the temperature, notice the temperature as 6. The temperature does not change. The temperature remains as 0 at this point. So that's what we call latent heat of fusion. So I just want to quickly state it, even if it's not there. Maybe it's still there, but let's just know what is latent heat of fusion. It's called a Heady heat that you don't see, but that is required to melt a substance, to change a substance from solid to liquid, to change a substance from solid to liquid without change of temperature. Can you imagine that? Something will change from solid to liquid without change of temperature. It happened very quickly. It doesn't mean you were not heating it. You were heating it, but in between, there is just a glimpse whereby the substance will finally quickly change from solid to liquid without change of temperature before boiling will start, before it eventually becomes liquid, okay? At C, all the solids have melted. At point C now, all the solids have melted and they become liquid. So as you are heating the liquid, it's still liquid till it gets to 100 degrees Celsius, till the temperature rises from 0 all the way from the bottom here. This is called heating curve. This is called heating curve. You should be able to draw heating curve and explain it in the exam. Okay? So this is called heating curve. So at point C, the temperature starts to increase. Temperature starts to increase, and every substance here is liquid. There is no mixture of solid and liquid. Everything here is liquid till the temperature reaches 100 degrees Celsius. When it reaches 100, at point D, then all the liquid, there is a mixture of liquid now and gas, liquid and gas. Meaning some of the particles have changed to vapors. The author did not include. If you go up beyond here to this place, and we say there is F here, then everything is now gas. Here is gas, this place. Here is gas. Everything has changed to gas. Everything has changed to vapor or steam. The whole water has changed to steam at this point. Okay, it's gas. But here, the temperature remains. Here we call latent heat of vaporization. Here it's called latent heat of vaporization. Here we say latent heat of fusion. Latent heat of fusion. The amount of heat required to change. Here is the latent heat of fusion. Amount of heat required to change a substance from solid to liquid without change of temperature. Here it's called latent heat of vaporization because you are changing to vapor, water vapor, or you are changing to steam. The latent heat of vaporization is the amount of heat required, Heady heat. You don't see the amount of heat required to change a substance from liquid to gas without change of temperature. Without change of temperature, latent heat of vaporization. Okay, I hope we done justice to the heating curve. Now let's quickly take a look at the cooling curve, and then we call it a day for today's class. What happens to the temperature when material change state? Here, the graph is coming down. Just now we are going up from solid at the bottom here. We are going up. So you have to. It's very important for you to learn this heating curve and cooling curve, and to be able to explain it, to know it, and be able to explain. Now here, at 90, this is gas. This gas. They'll say, oh, 90 is below 100. No, because this substance is not water. You know, so like for example, alcohol boils at 78. So beyond 78 is already gas. Beyond 78 is already gas. So when you see 90, they'll say, oh, this. It depends on which substance are we talking about. Which material are we talking about? Okay. So if this is 90, we say the substance is obviously not water. If it's water, it would be like we're coming all the way above 100 degrees Celsius. Okay. So at this 90 here, this curve, the first part is a gas. Okay. So you are cooling. You are cooling. You're not heating. You're cooling. You're cooling. Okay. So condensation takes place here. A point where here is only gas, where everything is now gas, and some of these has cooled to liquid, some are still gas. It's called condensation. This is called condensation. Condensation is the temperature at which the amount of energy required to change from gas to liquid. Is that okay? So we say the substance is condensing. It's condensing. It's changing from gas to liquid. Condensation starts at B, and end at C. Beyond C, everything has changed to liquid. C to D has changed to liquid. Now you can see here temperature is decreasing. Decrease from 78 to maybe 76, or what you call freezing. Temperature will remain same while the substance freezes. Okay, here is a mixture. During solidification is a mixture of solid and liquid till every liquid eventually change to solid. So beyond E, when you go beyond E, everything has cooled to solid, has solidified, has become ice, or whatever it is has blocked. Okay, so this cooling curve, you should be able to explain. Pause the video, watch it severally, and understand. Then, what is evaporation? You know, when you heat water, let's quickly talk about it. I think we end with evaporation and boiling. When you heat water, they gain average kinetic energy. Kinetic energy increases. And then not heating like you use a bossy burner. Like it leaves something outside to the sun. Okay, to the sun. The heat vapor, they'll be able to vaporize and escape. So when they escape, the temperature of this one drops. The temperature of the one remaining drops. Okay, it drops. So it will cause cooling. It will cause what? Cooling. When the temperature, the ones that gain more kinetic energy, escape from this surface, the remaining temperature, average temperature of the remaining particles will drop. So that's how evaporation causes cooling. Because evaporation will then cooling result. That's why when you go, someone is sick, you put a white cloth in a very cold water and put it on his forehead. If he has a fever, after you remove it for a while, because the particle of the water will get heat from his head and they will evaporate. When they evaporate, they take away the heat from his head, and then his body will cool down. Is that okay? Okay. Now let's why does evaporation cause cooling? I think I have explained this one. Because the average kinetic energy of the top surface have escaped. So the remaining particles now temperature will drop because the one with higher temperature has escaped. The average temperature remaining has dropped. Therefore, cooling will result. Here's an experiment to illustrate that. Okay, you set up a fan. You fan the escape, and then the temperature of this one remaining will drop. Okay, so this is an experiment for you to investigate this one, and then the last we compare. This is very important in the exam, the difference between boiling and evaporation. This is very, very important. You need to know the difference between boiling and evaporation. Boiling occurs at a particular temperature. Evaporation does not have a particular temperature. Evaporation occurs at any temperature. Because evaporation means you leave the liquid outside to be gaining kinetic energy, to be gaining sunlight. Okay, it can happen at any temperature. But boiling at 100, pure substance boils at a specific temperature. For water, it's 100 degrees Celsius. For alcohol, it's 78 degrees Celsius. So one of the first difference between boiling and evaporation is that boiling occurs at a particular temperature. Every substance has its boiling point. Every matter has its boiling point. So evaporation, no, it happens at any temperature. That's number one difference. Number two difference is that boiling is very fast. You heat something after like 1 minute, 2 minutes, 3 minutes, 5 minutes max, the substance starts to boil. Evaporation happens very slowly because you just need something outside for someone to be heating. Could take the whole day. Could take, it depends. Could take several few hours. So it's a slow process. Evaporation is a slow process. So you should be able to tell. The difference that evaporation is a slow process, boiling is a fast process. Okay. Now another difference is that boiling takes place throughout the surface of the liquid. Throughout the surface of the liquid. Takes place throughout the liquid. Every particle will be involved. Evaporation takes place at the top surface. Takes place only at the liquid surface, the liquid top surface, Only the particles that are on top gain the kinetic energy and they will escape. Now, boiling, bubbles are formed during boiling. When you heat water, you start to hear bubbles. See bubbles when water is boiling. Evaporation do not have bubbles. Evaporation, you should be able to explain. This question is always in IGCSE most of the time. In multiple choice, in paper 4, and so on and so forth. You should be able to tell the difference between boiling and evaporation. Then, in boiling, temperature remains constant. Temperature is constant, yeah. Evaporation, temperature may change, okay? Temperature may change. Now, in boiling, external thermal energy source is required. You need something to heat it, like from your gas burner, bossy burner, gas cooker. You need whatever you want to create to boil it. This one you don't need. External energy source is not required. Just keep it outside for sun to heat it. Is that okay? So you'll be able to tell the difference between evaporation and boiling. So what are the factors that affect the rate of evaporation? The first one is what are the factors that affect the rate of evaporation? Okay. What are the factors that affect the rate of evaporation? Let's take a look at them. The first one is temperature. Of course, you know that when you heat a substance, it increases in temperature, gain average kinetic energy. When it gains average kinetic energy, the top particles that gain more kinetic energy, we have the energy to be able to escape. So temperature is the number one factor. So as the substance gains more kinetic energy, you're able to escape from the more energetic particle will be able to escape from the top surface. Be able to. So temperature is one of the factors, the first factor that affects the rate of evaporation. What this question rate means, what are the factors to consider if you want evaporation to happen? That's the meaning. What are the factors that must take place if you want evaporation to happen? Number two is the surface area. The wider the surface area, if you put water in a small narrow cup, it will take the key to come for evaporation to occur. That same quantity of water, put it on a wide plate, on a spread out plate, and put it outside for sun to heat. Evaporation will happen very quickly. So surface area is the second most important factor for evaporation. Then air movement. Air movement. You'll be surprised you dry clothes outside, there's no sun, the clothes still gets dry. So when there's air movement, it's easy for the particle to evaporation to take place. Okay, moving air removes the liquid molecule as soon as they escape from the liquid surface. Okay, it removes them as soon as they escape. So this makes the air surrounding the liquid. Okay, so these are the three most important ones that affect rate of temperature, surface area of the liquid. Three of them: temperature, surface area, and air movement. Air movement. These are the three factors that affect the rate of evaporation. So you should know the difference between boiling and evaporation. You should know the three factors that affect the rate of evaporation. So with this, we come to the end of today's class. Here are questions